There's more value in the connections outside of these talks than actually listening to the talks themselves. Like we've spoken to a lot of very experienced, very tenured people who have lots of, great stories and mistakes that we can learn from so that we don't have to make them as well.
My name is Nicolai Josuttis, and I want to tell you something. We have this track, Back to Basics, here at CppCon, introduced a while ago, because beside all the new stuff, we want to talk about the old, established, mature stuff. So that's a little bit funny to talk about concepts, because concepts are brand new. Well, as most of the programmers do not use C++ 20 yet. But I would say it's correct, it's right. This turns out, and you will see why, concepts turn out to be a key feature that improve the quality of the language and the quality of code a lot. And here you learn why. Assume you have a function template called add. Let's add a value into a collection. Both are generic, so generic type for the collection, generic type for the value I want to add or insert. So the way I insert it here is I call pushback. So I can call this function template with a vector and an int. Well, if it's a vector of int or similar. That will compile, so that moment we instantiate the template and everything is fine. Now let's try this for a set. And that doesn't work, that doesn't compile, because sets don't support pushback. You have to insert elements with insert. So the naive approach might be, now let's add another add function calling insert. But that doesn't work. Because now you have two definitions, two bodies for the same function, which is specified via having the same signature. So you cannot do that. Overload resolution will not accept that. Overload resolution, so the decision when we have a function call to decide when there are multiple candidates, which one is called, is done by only looking at the signature. Even ignoring the return type. So there are crazy tricks to deal with that. They are called SFINAE, they are called enable if. A lot of people who like angel brackets like this code, nobody else likes it. And nobody wants to program like that except the smart guys. Okay, so we finally now have a way to solve this problem in a proper way that doesn't, to some extent, abuse templates, which directly supports what we want. And that is, let's insert a line, and in that line, let's put a statement or clause requires has pushback for call T. That constrains the template. That means this template is only appropriate if the type call T has pushback. Now, what is hash pushback? Has pushback. Well, that's something I defined myself here. It's a concept. And so we are using concepts here. What is a concept? A concept is a name for requirements. So you see on the right-hand side the definition of the concept, which uses, again, the keyword requires with curly braces. And that's a way to specify a couple of requirements. So make sure you got it right, because it's a little bit confusing. The first thing is you have requirements. There are multiple requirements here. One is that we have to support pushback. But the way to read that is we require, assume I have an object of type called T, and I call this object C, So I assume I have C and I have V as a value type, an object of the value type of the collection, which standard containers support. That's the type of the elements. So I assume I have a type, an object that could be the element of the container, and assume I have a container of this type. Is the next statement okay? Or I should say, is the next expression okay? So is that valid code? Yeah. So we check whether pushback can be called. But by the way, this is not only checking for one requirement. There's another requirement here, check, which is type call T has to have a value type. Otherwise, it's also not valid. So this code has to be valid. And if that is true, then we satisfy the requirement. And the whole thing now gets a name. That means instead of writing this all the time, you can say, well, my concept has pushback, represents all these requirements. And so a concept is named requirements. It's a name for some requirements. And requires in the function call, in the function declaration, function template declaration, that's a constraint. We constrain this generic code so that it cannot always be used. It can only be used if, by looking at the signature, this requirement or this concept is satisfied. So that way, we now have an add in case we have has pushback support and another add that doesn't require that. I could also require there something like insert, but it's not necessary to solve this issue because there's a rule when two adds match, the more special one wins. So two function templates, when they match, the special one wins. And you see here, so for the vector in, both adds are available. The first one is available because has pushback is supported, and the second one is available because it's always available. And so both can be called. The first one is more special, so that is called for a vector. For a set, the first add is not available because a set does not satisfy has pushback, so the second one is called. That's the basics. The basic idea. Look at the place where we specify the function template signature, well, part of it. We just introduce the template parameters and we introduce the requirements, the constraints. You can write that in one line, and it looks like this. Instead of writing type name, you can write has pushback here. So for a call T that has pushback and a type T, just some type T, this add is supported. It means the same thing, it's just a different syntax for what you just saw. Good. That's it. We can end this session, but as usual, in C++, there's more to teach. There are interesting consequences of this little feature. So one interesting consequence is when you introduce a new feature, there's a new opportunity to make mistakes. So how about I misspell the requirement? How about saying, let me support pushback, but I forgot the underscore? It's interesting. What happens now? Does the code compile or not? Well, it's interesting what's happening. The first call of add at the bottom will not compile, and the error message is, I cannot call insert here. What? Yeah, you should not call insert. So why the hell did I do that? Well, remember the rules. We said, here we have requirements that have to be met. Well, my vector does not support pushback without an underscore. So the requirement is not met, so the concept is not satisfied, so the constraint of add is not fulfilled, so you cannot use the first add. You have to use the second one. So we try to compile this code with insert, which leads to this error. So if you write concepts, it's good that you check that concepts work. Every code needs test code. How can we do that? Well, you know, concepts are compile-time Boolean values. And there's a way that means, in other words, the whole requires expression here gives you true or false, depending on whether it's satisfied or not. And the concept gives you back true or false. So you can just use a static assertion, a compile-time assertion, to say, does has pushback used for vector in satisfy is satisfied? Is it satisfied? And is it not satisfied for a set of in? Great, you should do that. Now, let's come back to the starting code. We have the function template, no constraint yet. We have the vector, everything works fine. There's a new syntax for that in C++20. Instead of using template parameters, I can use auto. You might know that from numbers. You might have seen that already in C++. This is a way you can use auto now for each and every function declaration, which makes the function makes it a function template. This is generic code. So this is just an abbreviated function template, equivalent to the code you see on the right in the bubble, except that you have no name for T1 and no name for T2. So that means, by the way, that this definition, usually that means the whole definition, including the body, belongs in the header file, and no inline is necessary when you do that. Okay, let's come back to concepts. We run into the same problem when we use this feature. When we have another add, because that to call insert, because we cannot use the first add for a set, it's an error. We have two definitions of add. So how can we constrain this? Well, you just qualify auto with has pushback, which you have seen before, which is equivalent to has pushback used to be qualifying T1, so that we have a constraint for T1. So here we have a constraint for the type the collection uses as reference. You write it directly in front of auto. If you have a const auto reference, has pushback would be between the const and the auto. Concept, as we have it, is here. The requirements are there. So again, we have requirements, concepts to have a name, and then we apply this to auto. We call this a type constraint. When you directly qualify a template parameter or auto, this is a type constraint. And overload resolution now says the first add is more special than the second, so that's preferred. Same as before. By the way, side note, you might wonder, well, when I have a template parameter and I use a member that is a type, I need type name. That's no longer true in C++ when it's clear that it is a type, which is not always the case. So it's an interesting question when you still need type name and when not. But it works if you forget it sometimes, as here, for example. Good. Can you have requires clauses that are in front of auto? Yes, you can have them, because you can have requires clauses behind, at the end of the signature. So that's interesting. So we can now use the type of the collection by checking, well, the decal type of the collection has to support pushback. Unfortunately, that does not compile. The error message is, I cannot call insert. Why? What is a type of call? When I call decal type for call, what is it? It's a reference, yeah, not an R-value reference. It's an L-value reference, yeah. So the type of call is not vector of int. The type of call here, the decal type of call passed to has pushback, is std vector of int reference. Can you call for that pushback? Yes, you can. But it's not allowed to use a member called value type. References don't have members. So that doesn't work. That's not valid code. And you learned that as it is not valid, the concept is not satisfied. So the constraint is not met. So for the vector, only the second add is used and compiled, and that leads to the error message that we have a problem with the insert. Good. How can we solve that? Well, we can remove the referenceness when we pass it to the concept. Well, you might be used to use decay there, std decay, which decays a type, and it's a shortcut because it removes both constant, volatile, and references. We have a new type trait here called remove cvref in C++20 because decay also converts arrays to pointers. This is not always what you want. So this is a new type trait, and it will be used a lot. This places burden on those who write the add function. Can we do it somehow better? Can we make the concept more flexible? Yeah. Well, declared here that it's a value type member when you ignore the referenceness of a call t parameter. And it works. Once again, you should have a test code for that. So your test case should be, can I call has pushback for std in reference, and is it satisfied? So is the answer then true at compile time? There's another way to deal with the element of this collection, which is a utility we introduce in C++20 with the ranges library. Ranges and concepts play well together. Ranges use a lot of concepts, and concepts help to improve the quality of the ranges library. So in the range library, there's a utility called give me the value type of the range. Unfortunately, all the stuff of the ranges library is in a different namespace because we would get too much trouble with collisions and we are backward compatible. So not in this case, it would be break some code, but we have other stuff that would break code. So that utility gives you the type of the elements in a collection. It will also works for references and even for raw arrays. You need a header file for that. Okay, maybe what we test here is, can we add, does the container push back, support pushback for its own element type? So maybe there's a better approach, which is, why don't we just check, can we add that value into the collection, including type conversions and something like that? So it's possible. The concept can support multiple template parameters. So we here constrain the add that it should be possible to push back, to be able to push back a t in a call t. Here's a definition. That's a concept for multiple parameters. Concept can push back requires that assume I have an object of call t and assume I have an object of the type of the type of the thing I want to insert. Can I call for that pushback? Yeah, that's better. Can we still use auto here? Yeah, you can say, well, that's a little bit tricky. You cannot easily apply, sometimes you can, template concepts with multiple parameters to auto. So you would write something like this. requires can push back for the type of the collection and the type of the value as we instantiate in the concept the objects and just as they are with that type. Doesn't matter whether they are values or references. The code is just fine. We don't use a member value type here, which was a trouble, causing trouble for references. Okay, 20 minutes, done. Don't do that. Don't do that. This is a problem of people who teach is you have to understand a feature and then we can discuss how to use it. So don't introduce a concept answering the question, can I call pushback? Because your function template does not call only one thing. We have 100 different calls, and if we have a concept for each and every call, then yeah, you can do that, but it requires here the clause would have to say can pushback and can call size and can output and can swap and can. It's a logical operation. Concepts are Boolean compile time values, so you can combine multiple constraints with and. That's fine, but it's boring. And you reveal details of the body of a function and put it in the signature. That's also not good to do. So instead, it's better to have coarse-grained concepts. Something like this, where we say, I have a concept for what is required to be a sequential container. Well, here we can see we define it in an interesting way. First of all, we say it has to be a range. That is using a standard concept. So in the standard library, we provide a couple of concepts you might be able to use in practice. And one of them is this. The requirement here will check whether we can iterate over elements with this thing, on this thing. So in effect, can we iterate from begin to end? You will see that in a moment, that concept. That's a Boolean expression. So with and, we can now add additional requirements. And you see here by saying, let's not use references here directly. We should be able to push back. We should be able to pop back. We should be able to begin to insert at the begin a value. We should be able to erase something with an iterator. It's not important that you pass begin here. Don't get me wrong. We don't check, can I erase something at the begin only? This is a compile time feature. So begin represents an iterator. So the question is, can I pass an iterator as it would be returned by begin to erase? Is that what compiles? Can we call clear? Can we, that's interesting, can we here declare an initializer list for that? Well, be careful. I should be careful here. This is not a declaration. This is a temporary, creating a temporary object. A declaration would not be allowed. It has to be an expression. So you have to do it that way to say, I want to be able to call a constructor that way. Can I have an assignment? And here you see you can do even more. Where can I call less than? And then is a result satisfying another concept? Convertible to is another standard concept. So can I convert the result to bool? So you cannot say equals bool, but we have a concept to say it has to be bool, then it would be called SCD same as. Okay, and so on. So multiple requirements are here combined into a general purpose concept that could be used in various places and help to find whether we have this. And then it can be used as you have seen. We don't have such a concept in the standard, by the way. We have similars like range, you saw. Oh, and let's look to range, to the range concept. Let's look inside the standard how it is defined. So here it is. Concept range requires that for some object of type T, I can call begin and end. Well, you don't call a member function begin and end. std ranges begin and std ranges again are still helper utilities. And these helper utilities might look whether I can call the member function begin and end, but they also look whether there's a global way to freestanding function begin and end I can use, or they even check if it's a raw array, and begin and end would then, for the array, return the address of the first and behind the last element. So this range concept is also satisfied for raw arrays. It's interesting. When you look at the standard, that's not the only thing we specify for this concept. We specify a few more things, but not in code. We specify in text. So let's read what we say there. Type T models range only if the half-open range between begin and end for this T denotes a range. Both begin and end are amortized constant time and are non-modifying. And in case begin models a forward iterator, then begin is equality preserving, which means if you have two iterators pointing to the same spot and you increment them both, they again point to the same spot. This is nothing we can check at compile time. All three of this is nothing we can check at compile time. So the first thing says, is it a range? For example, requires begin should be in front of the end. And they should refer to the same object. Yeah, that's nothing we can check at compile time. That's a runtime requirement. And the second one is a performance requirement, at least the first part of it. So amortized constant time means begin and end should be reasonably fast. If you wonder why it's not constant time, look later on my talk here at CppCon about why. What did I give yesterday? I'm old. Oh, views. Yeah, thank you. I'm jet lagged. And the other thing is begin and end are non-modifying. That's also nothing you can check. I mean, you can check is it const, but if it's not const, it's not clear whether we modify or not. So that's something that we describe as a requirement which cannot be checked by a compiler. And the last one either. So concepts can specify semantic or runtime or non-functional requirements. They cannot be checked by a compiler. The reason we have them is they document. So in this case, the concept only documents what we expect from a range. And with that expectation, we also can say if somebody has a range, they can expect that begin is reasonably cheap. Okay? Good. What else? Let's come to the two use cases of using the keyword requires. Yes, we use requires for two different purposes. So one time it's used to specify requirements. One time, it's used to specify constraints. The major difference is curly braces. If you have requires with curly braces, it formulates requirements. The parameters are not necessary. If you have them already, that's fine. We don't like to introduce multiple keywords. So we could have said the second requires is called constraint, but we don't do that. But this has an interesting consequence. I told you, you don't want to have a concept for each and everything, but maybe in this add function, without introducing a concept, we want to make sure that the right add is called. How can we do that? Well, it's compile time Boolean values that are used, and it's compile time Boolean values that are required. So we just say requires. If I put away the colors, it looks even more weird. That was something we discussed a lot when we standardized C++. Nobody liked that, but finally we did it right. We have other examples in the C++ standard library where we try to be cool and we cause problems over problems. For example, 2 ampersand in the declaration might be an out value reference if it's a type in front, or might be a universal reference if it's a template parameter in front, and they have different rules. So that's good. 2 times requires, now you know why. It might have been better to say the first requires is called constraint, but we have it that way. And you don't write this code very often, but you can. But let's come back to the point that requirements, concepts, compile time Boolean values, and constraints process compile time Boolean values. So the only difference we see here in this generic code is the call of pushback or insert. That opens an opportunity to write this code completely differently. Let's write one function. And in that function, we do the following. We use a compile time if, and that compile time if has a compile time condition, which is pushing back that value in the collection required, supported. So that's a requirement for the then branch. Then we call pushback. Otherwise, we call insert. Awesome. I'm sure everybody who wrote in the past templates sooner or later wanted to have an easy way to say, if this is supported, do this, otherwise do that. We have it now. That's great, absolutely great. Please also note, this requires in the yellow box does not use parameters. We have the objects already. We don't have to say, assume I have an object of this type. So it's that short. And if you want to, in if context, we have multiple requirements, just provide them with and. So requires this and that and that. Great. I love that. If context, when we standardized it, it was very close that we accepted it for C++ 17. It turned out to be one of the most powerful features we ever standardized. It solved so many tricky stuff. Let's make a mistake. Let's use this add and use a set of string, but we add 42, which is obviously an error. Well, the pain caused by this error you have seen before, I bet. So you get an error message that, well, explains you that somewhere in the deep darkness of the code where you then call insert, you have a problem. So I did some highlighting here to help you. But yeah, so there's no known conversion. you have to find this place in an error message of 100 lines. You know that. The problem is that once we decide that we call add, then we compile this, and there's a problem. There's a problem inside. So why can't we, in the specification of add, specify that there are additional requirements? Obviously, a requirement is not met. And the requirement is that the type of the value we insert or add has to be convertible to the type of the elements in the container. Yeah, you can do that. We have concepts for that. We have standard concepts for that. We have std convertible to, and that says, give me the value type of the collection. Could I convert it to t? The otherwise rounds are thought. Could I convert t to the value type of the collection? With that specification, this is still an error, but the error message is way better. Well, first of all, there's a way even to put that and constrain that in a parameter. You might see convertible to uses 2 template parameters. I told you that's a problem to use this in front of auto, except one of them you pass. So you can do the following. You can say the first template parameter called t has to be arranged, and the second t has to be convertible to the value type of the call t. Great code you can easily read. And now see the error message. The error message is still there, but it says, depending on the compiler, of course, there's a candidate I could call. I cannot call add here. It's only one add we have now. There's a candidate that's ignored because the constraint is not satisfied, because std convertible to from an int to a set, the value type of the range evaluated to false. Great. Do you like that? So you can also applause here. I tell the designers of these features. And by the way, the quality of the error messages here are different in the different compilers. Clang is the best. And then Visual C++ and GCC, you can help a little bit. They are a little bit too cheaty, talking too much about the error sometimes. Too much information is sometimes an issue with GCC. But they work on that. And they appreciate if you come and help them. So, concepts. You've seen most of the things. And usually I end up with an introduction, but I have 20 minutes left. Great, so we can have some fun. So first of all, you saw we have requirements, we have concepts, we have constraints. Constraints can be applied by using a requires clause or by directly constraining a template parameter, or auto. Please remember, no code is generated. This is done at compile time. So, which, by the way, takes time. So compilers need time to do all these checks. And we have other new interesting issues that can happen. So one is, you have two concepts here. One checks for hash size, and one checks for whether we can use an index operator for a type called t. So now let's assume we have a function foo that requires that size is there, and the other that we require that we have an index operator. Why the hell we do that? Well, if you have a list, this works fine, because a list has no index operator. So it's clear that only the first foo can be called, but not the second one. So we call that. But if we pass that to a vector, that's an ambiguity. So we have now two templates, function templates, both have a constraint. But it's possible to specify a hierarchy of constraints. it's possible to say, but you have to say that, specify that explicitly. So you could say, for example, that my foo has a constraint, but this constraint is more special than the constraint for the first foo. So we require has size and has index of. That will work because that's now more special than the other. We say has size and has index of subsumes has size. Please note, only concept constraints are checked for subsumption. If you have a concept called this is a big type, more than 8 bytes, and another concept that says this is a big type and a class type, this one does not subsume the other. So if you have two functions, one taking a big type, the other taking a big class type 0 here, the call of foo is ambiguous. But if you do the following, if you say big class type is big type and in addition a class type, this does subsume the concept big type. So now if you have both foos here, that will be resolved, the ambiguity, because foo2 is more special than foo1 if both things are met. That is done logically and indirectly. So it's not only that we see this is textually an extension. We really look whether, if we look at the primary concepts that are required, why one concept can require another concept or can require another concept, whether one set of requirements of concepts that are required is a subset of the other. So look at that. We have here now big type and class type. I could specify, is it a big or class type? And I have a concept, is it big and class? Obviously, the second one, the last one, is more special. And that's checked. But that takes time, that takes compile time. Especially if you have or in concepts. Be careful a little bit. Or in concepts may have a significant impact on compile time. Because now we have even not to look at one subset as the other. We have multiple alternatives to check. And so we have multiple checks to do. But we use that a lot in the standard library for our standard concept. So here, let's look a little bit in the C++ standard about subsumption hierarchies we have. So we say if a type is copyable, that implies it's movable. That is what we require in the standard. So we define copyable as movable and some more stuff is possible. We have semi-regular, implies copyable, subsumes recopyable, regular, subsumes copyable, and semi-regular. Regular is you can declare, you can assign, you can copy, and everything works fine. That is what a type usually should have, according to Sean Parent. We have, for that, a little bit of primitive concepts here. You should not use them directly. It's just that we, by using different concepts, different composed concepts, we end up with clear subsets where we can really see one is the subset of the other. We generate from that others. And for example, this is used then to specify the hierarchy of iterators. So we have an input-output iterator. That is, you can do both. You can do either one. In principle, one of this is supported. So that means you can go forward, can call begin and end. But it's not clear yet whether we read or write. Then we have output iterators to write, input iterators to read and forward, to go multiple finds over the collection, bidirectional to go backwards, random access to jump back and forward, and continuous iterator requires that the elements are in continuous memory. For that, we have other constraints, and a forward iterator is a way to specify permutable, and that is to specify to find sortable. because then the iterator of that, where you check that from, can be used to jump around to define things. That's a technique in itself. A lot of power went into the definition of these concepts, and sometimes it's hard to understand why they are defined that tricky. I know how often, when I wrote the book about C++20, I asked in the reflector and in the community, why the hell are we doing that? And it works. That's a good thing. Like printf works, and formatted output works, and coroutines works, and you don't have to know all the details. Use these standard concepts. And of course, the burden is to learn about these standard concepts, to have a good feeling about what standard concepts are there. Most of the time, we supported things like range processing, and then function calls, and a few basic things like is an integral type, or is a fundamental type, or whatsoever, or type comparisons. Nice thing here. We never subsume automatically. So subsumption has to be specified explicitly somewhere. So this is a famous example we discussed when we standardized concept. Somebody, I don't know who it was, came up with this example, said, assume we have a concept that specifies the requirements for geometric objects. Now, here we specify only one for simplicity, which is I can call draw. And let me have a print function here, and that print function requires that the parameter is a geometric object. Obviously, now if you have a type that supports a call of draw, it's a geometric object according to this specification. So a circle, you can call this print because it fits. Now, we have to talk about cowboys. Because cowboys can also draw. Which, for those not familiar with native English, as me, I had to learn that. Draw means take the gun. Which is probably semantically not the same as for a geometric object, the draw. We have specified here something more special. We said, and in addition, we require the assignment operator. It's not that the circle does not support assignments. It is that we don't require that for geometric objects. So if we would now say a cowboy subsumes a geometric object, we would say, yeah, a cowboy is a special geometric object. This might be true in some computer games, but not in general. So the fact that we don't automatically subsume means that the print call here now gets ambiguous, and that is what we want. We want here, yeah, we now have a print for cowboys and a print for geometric objects. That's an issue to solve. By the way, here you see another reason why concepts should be coarse-grained. Because the more things you require, the less likely it is that you have a specification that does accidentally fit. You're getting more precise about the requirements of this type. If you want, for some reason, that a cowboy subsumes geometric objects, you can do so. You can say cowboy subsumes geometric objects by in the specification saying that, or in the print function you can say, I have here a version that is for those who are both cowboys and geometric objects, and that will be preferred over the others. Okay, almost done. Finally, let's look at where you can use concepts in your generic code. You've seen most of the time here, if not always, function templates. But they can also be used for class templates, alias templates, variable templates, and that is something to look at. It can only even be used for non-type template parameters. The only thing you cannot do is you cannot apply concept to concepts. I'm sure sooner or later somebody will ask for that feature, coming up with some crazy way to program. Good. I want to show two things here in the last 10 minutes. One is constraints for member functions. If we have a class, you see the class here, my type. This is a generic class. This class internally has a value of type T. So it's a class template, so we have a way to use that for my type of double or my type of string. And for both, in both cases, we can call print because we have a member function for this type defined as a class template. What you can do with constraints is you can say there is a constraint in my member. You can say this member function is not always available, only sometimes when certain conditions are met. So here we require that type T is either integral or floating point using concepts. We have similar type traits. There you could use is arithmetic, but I'm using concepts here. That has the effect that only for my type of double is 0 is available. We have a lot of times in C++, even in the standard library, we have similar generic types. We have types that have some API, but under some circumstances, we have additional member functions. Atomics are a good example. Atomic int has more member functions than atomic pointer. We have to specify multiple class templates for that and use techniques like partial and full specialization, tricky in themselves. So here we have one class, and we say, yeah, but some of these members are not always available. A very typical thing is you say, it's available if my type T supports it. So here's how you write that. I support is empty, and I have a constraint which is a requirement that I can call for this value empty. Great. So we delegate the availability of this member function to the availability of the underlying type. I like that. And we use that already a lot in the standard in the C++ standard in new types that are standardized now. Like, for example, the basic interface for views is using this technique a lot. Finally, let's talk about constraints for non-type template parameters. Here's a function you can call at compile time. It gives you back the answer of whether the passed in is a prime number. Context to make sure we can use that at compile time. Can we use that as a constraint? Yeah, we can. You just say here, in my class, I have a template parameter, which is not a type, it's a value. That value must be a prime number. And C1 here, instantiated with the value 6, will not compile with the method that this constraint is not satisfied, while with the value 7, this will compile. That will help us a lot. Think about security code where parameters have to be prime numbers. And of course, there are way other examples. Two things here. First of all, when requires a constraint is non-trivial, just a concept or very trivial Boolean expression and a combination of it with and or, you need parentheses around. So you might be surprised here to see that. Sometimes that's necessary. We could not skip that because of backward compatibility. And then the question is, can I have a concept for that? Yes, you can. So can I give this requirement a name? Yes. Here's how you do that. For a generic value, the concept is prime checks if the value is greater than 0 and is a prime number using the CppCon function above. All of this is then evaluated at compile time when we, for example, require that a class requires that this is a prime number, and then we get the same errors, but with the interesting different message. If there's an error, we will not say that for some reason the constraint is not satisfied. We will say the concept is prime is not satisfied. Great. Do you like concepts? Do you like them a lot? Say yay. Yay. I think it's good. I mean, a couple of programmers don't write concepts ever, they just use them. But at least you get improved error messages. And it helps us to do a lot when we do generic programming. That's it. Thank you very much. I think we have a few minutes for questions, and this is the advertisement part. This is part of a book, of course, and it is also, that might be interesting, part of a training I give and the next time, upcoming Monday and Tuesday, as a CppCon Academy training. You can still register. But now, if you have a question, please come to the mic, and I'm happy to answer 2 or 3 questions.
Yeah.
Yeah.
In some of your examples, the code's duplicated in the bias clause and then the body after it. Is there a way to avoid that level of code duplication?
No, we don't have support for that. Yeah.
Would there be support for that?
I don't think we will have support for that because this is like const-expert. When we in const-expert said const-expert can be deduced by the body, we say, yeah, just look in the body at if all the calls are const-expert, then we can deduce that the whole thing is const-expert. But that's not the way it works. Sometimes we require something in addition, and sometimes we say, yeah, maybe a local call requires const-expert, but we don't care because we know we will never come to that situation where an exception can be thrown. And I think it's similar to here. I think we want to say that the granularity of a concept should not directly map the code. I don't see an early way that we say that it happens so often that we just duplicate the code that we have that. No, we will in concept only check for the usual typical things. We will have more coarse-grained concepts. We don't want to have many concepts. Otherwise that takes compile time. So I don't think we get that, and I don't see a need for that. It's some issue. You have to say you formulate the concept, but as I said, it's usually on a different granularity than the precise code you have. And we decouple, to some extent, the body from the signal.
I noticed yesterday your ranges talk that, well, I guess today you mentioned that there's a standard concept for ranges. You can call ranges begin, ranges end on the input range. And if that's satisfied, then the concept is the range. But one of the things you mentioned is the written standard for ranges, begin has to be const, and you can't validate that at compile time. But if you apply a filter to it, I believe you were talking yesterday, you mentioned that begin isn't constant in that case. So I'm curious how those two play together.
Exactly. Well, let me go to that definition. So a view, you cannot use a view when the range is const. That is not what we check here. We check that when we call it, it is not modifying the underlying value. So that's a different thing. And this range specification is fit for all views. A view is a range. So we have a subsumption saying std view is std rangeless view is an std rangeless range. So no, that's not a problem.
Okay, cool, thanks.
Okay, thank you very much. I hope you liked it, and I hope we see you again and you learn more and enjoy the rest of this conference. Thank you very much.